and extrapolated it 10 years from 1965 to 1975 from 60 components to 60,000 components on a chip.
First thing you have to tell him is, guys, we've been giving you a free ride for 30 years while you write your crummy software and we made it faster. Right? That's over.
The future is parallel. Single cores are not getting any faster.
All right, good morning. I'm so glad to see you here again. Well, it has been a week since we last met, but I believe you guys must watch the YouTube video that I put online and join the talk by Joe Emmer. And thanks everybody for attending the talk. I think it's a really great talk. So before we start, what do we want to talk about today? You know, like these days, we are in a point that we have to make a lot of choices. So that's why I played the song "One Thing Right," because you know this week, or actually every day, every time, you have to make a lot of choices and you have to make one thing right? But how do you know if the choice that you are making is right or not? Well, sometimes it's case by case, but in terms of writing code to optimize for cache performance, what's the one thing right to do? You must not miss this lecture. So before we start, I know it has been a while since you guys were in the class. So we always want to make sure that we are on the same page before we start. So that's why I want to spend time doing some recap slides before each lecture. So first of all, why we are here, right? So it's very important that whenever you want to make a decision, you want to do something, don't forget where we are coming from, right? So the reason why we are here is because we are talking about there are two important components involved in a machine, the processor and memory. And because the processor and memory in terms of latency, as you can see from this graph, the performance has a really huge gap here, right? So if you have no way to make the memory better, there's even though how your processor is really fast, the majority of the performance will be burned in accessing memory, especially if you remember, right? Every instruction, every data, we need to access the memory. So that's why we built memory hierarchy. So the basic idea of memory hierarchy is that instead of solely use DRAM as our backup memory storage, we use SRAM as the cache, which is a small pieces of SRAM capture the most frequently used data or the data that may be used recently. So that if we do a good job on this, most of the time your processor only need to consult the SRAM for the data that I want to use. So you can imagine that SRAM is like your secretary. So the secretary knows what you want. The secretary knows what you may want, right? And the secretary knows what you like the most. So every time you just ask the secretary to give you the stuff. But there are cases that the secretary may not capture that. So it will take more time for us to access the DRAM. Well, and sometimes if you are a big boss, right, you know that, well, one secretary is not enough. So you want many secretaries. So that's why we have multi-labels of cache. All right, so that's what our memory hierarchy looks like. And whenever we read data, don't forget, we got the address, but we have to partition them into tag, index, and offset. And the reason why we have offset is because the cache is organized in block. So you have to tell the cache which word, which byte in a block that I'm looking for. And that's the meaning of offset. And there's an index field, tells the cache which set of blocks that may contain the data that I'm looking for. And the tag is the identifier of the cache block that I am looking for. So if I use the index to find out what are the possible blocks that may contain my data, but no one matches the tag, it's a miss. But if you're lucky, you find a matching one, that's a hit. So whenever there's a miss, you have to go down to a lower level memory hierarchy and repeatedly until you find the data. And whenever we found the data in a lower level memory hierarchy, we have to place the data in the current level of the cache. However, there's not always the case that you will find a free block. So you have to kick out somebody out. And when you kick out somebody, that block may also be polluted. And if you don't write it back, there's no way that we can preserve the modified data in the system, meaning that you are going to lose your execution result. So that's not good. So we always have to write back if the data is polluted. So that's what happens when you read data. And when you write data is also similar, except you have to set dirty bit when you are modifying the data block, because that's the only way that we know if the data has been modified or not. So that's what happened when we read write data. So another thing that is important is that how do we know the item is found in a data or not, in a cache or not, is that we have to follow the process of cache lookup. And I'm just briefly giving an overview of what happened, but right now let's dig into the detail. So whenever you receive an address, you partition the address into tag, index, and offset. And we use the block offset to figure out where in the block the requesting word, requesting byte, the requesting double word may locate it. And use the set index to find out the set of blocks that may contain your data. And we use the tag to see if there is any block matching the one that you're looking for. And if there is one, then there's a hit. Otherwise, it's a miss. You have to go down level. And in 2 lectures ago, we talked about there are 3 types of misses in cache. The first type is compulsory miss, cold start miss. The first time you access the data, there's no way that we know you want this, right? Even though you have a good secretary. So that's compulsory miss. And capacity miss is because your desire is just too big. So there's no way the cache can ever satisfy that, right? So the working set size of an application is bigger than the cache size. No matter how you reorganize the cache, as long as your cache is not big enough, it's going to be a miss. That's called capacity miss. And conflict miss is the case where well, it's not about capacity. It's just because, remember that, a block can only go to limited number, can only go into a set. And if the set does not contain sufficient amount of entries to accommodate all blocks that you requested, that would be mapped to the set. There will be a conflict miss. So that's the 3 different types of misses. So if you know the whole idea of cache design, you will figure out that, well, sometimes some of the code like this is very natural. However, if you are not aware that the memory hierarchy design of your underlying processor, it could be a disaster. For example, like this processor, it has a 64 kilobyte two-way set associativity, 64 byte block cache. And turns out that everything here will be a miss. So so that's why a memory hierarchy is so important for performance optimizations. In the last lecture, we also talked about that. Well, memory is not just what you see, because we have the abstraction called virtual memory. So to support virtual memory, and the most efficient way to support virtual memory in hardware is that we made our cache virtually indexed, physically tagged. And the basic idea of virtually indexed, physically tagged cache is for an address, the block offset and set index, they must be located in the invariant or say constant part before and after translation. So the set index and block offset both together, they must be exactly the same with your physical, the page offset with your virtual page size or say physical page size, because they are all the same. And the only thing that will change would be the virtual page number, which will be exactly used as the and the virtual page number will be translated into physical page number, and the physical page number will be used exactly as the tag in your cache. So what happened when you access the virtually indexed and physically tagged cache is that we still use the set index from the virtual address and a block offset from the virtual address to access your cache. However, at this point, we do not compare the tag. We just use the TLB to look up the virtual page number and what's the physical page number that's mapped to that physical page, virtual page, and use the physical page number as the tag to compare with the tag in your cache. And if they are consistent, then there's a hit. Otherwise, we will have to go down a level. And if your TLB cannot find the translation, there will be a TLB miss until we can compare the tag. So that's why TLB miss is so expensive. And that's why in the last lecture, we talk about optimizations for that. Okay, so it's always good to know our standing. And right now, our team scores are really close. So every team still have a chance to get a gift card from Amazon, well, at the end of the quarter. So so let's keep our discussion. Let's still spend keep going with your discussion, and I believe all of us will have a good ending at the end. All right, so this is what we are going to talk about. So today we are going to talk about architectural optimizations for cache performance. And as I mentioned, the most important factor in affecting performance is actually programmer. So as a programmer, what can you do? So before we start, let's start with some basic hardware optimizations in improving 3 Cs. So as I mentioned, we have 3 Cs, right? So and we also have ABC, like C equal to ABS, right? So we have ABCs in our cache parameters. So how this can help us in improving the cache performance. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so well, this is the current standing, but you know, sometimes majority may not be right, and the two that you think might not be the two that other people are thinking. So why don't we go ahead and have a group discussion, and in the meantime, don't forget to pull up the screenshot that I just sent out. So now let's go ahead and start your discussion. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so it's after discussion. Well, C is still the most popular answer, but we also see a trend that D is increasing. So let me pick one group to share your thoughts with us. So it looks like we are having mistakes, or say group 2 in sharing your thoughts with us. So who is the scriber of your team today? Please raise your hand and share what you heard from your discussion. All right, I have Joshua.
Hey, Professor.
Hey.
We were between C and D. We were confident that one and 4 were true.
1 and 4 were true. So why do you think 1 is true?
Sure. So when you increase associativity, you just increase essentially the number of buckets per set, you could think of it as. And a conflict is when you're conflicting because there's no more buckets left, so you have to kick something else out. If there's more buckets, it's less likely that you'll have that conflict.
Right, and we also have a walkthrough in the previous lectures, right? So even we have the same amount of entries, but if I change the weight associativity to 2 ways, then it significantly removes the misses in direct map cache, right? So you see that, right? So how about the other one that you think?
So for 4, increasing block size can reduce compulsory misses. So compulsory misses are like, it's just not in the cache. There's not a conflict, but it's just not there yet. If you have a bigger block size, more data will be in the cache. So if I'm looking for some item, it's much more likely it's already in a line if those lines are bigger.
Okay, so how about 2 and 3?
So
what do you guys think?
One of our team members made a good point for 3. We just weren't sure. They made the argument that if you increase the block size when you do miss and you have to bring a new block into cache, because it's larger, it may take more time to copy that block into cache.
So that is called miss penalty, right?
Yeah.
So that one is correct. So how about a second?
Increasing. We didn't think that was true.
But why?
So if you increase associativity, right, you're going to increase the number of hits, but you're not going to make the process of hitting that data any faster. Right?
Okay. Yeah. So here's the thing, right? So for this question, right, it's actually, if you increase the weight associativity, you could potentially increase the hit time, because think about like you have to fully charge all your bit lines, and you have to look for you need more muxes to look for. To select what way to compare, right? So your circuit is increased, so your hit time will be longer instead, right? So increasing the weight associativity is generally hurt the hit time, which means that your processor may be running slower if you don't do it correctly. And for the block size, as you mentioned, because every time you need to fetch more data and replace more data, so the miss penalty is going to be larger, right? And for the last, whenever you increase the block size, because you bring more data into the cache, so it helps us to reduce the compulsory misses. So for this question, the right answer is actually 3. So this poll gives you a very good idea that majority is not always right, and even the poll itself doesn't represent the truth behind behind the world, right? So don't be amazed by other people's answer. If you think you are right, if you think that's one thing right to do, go ahead and do it, right? And again, like our midterm is coming up, right? And I know a lot of you were looking for it, and one thing I can tell you, it's an open book. It's a take-home test. You might want to consult your friend, but first of all, it's not legal because it's considered as cheating. And the other thing is that even though you do that, right, as you can see from so many examples we have in the class, your friend might not know better than you do, right? So why do you ask them for that, right? So for this example, right, hopefully now you have to think through carefully for each question that has been asked, and you will figure out that maybe you know more than others, right? So for this question, the answer is actually D, the second most popular answer. All right, so now you know that, well, through reconfiguring the cache, through architectural optimizations, we can potentially improve the cache performance. So how can we save this guy? Right, so for this guy, we are executing a very frequently used snippet of code, but performance is really bad. So that's why I pull up this paper for you to read. I don't know how many of you really dig into the paper, but it's a very significant paper. a paper in memory hierarchy design. Noam Joby, he used to be with HP Research, and if you know some history about the Intel processor design, HP were like developing processor with Intel together, and HP is using those processor in their server market, and Noam Joby is the guy who lead HP's processor develop team. But later on, as you know, like a lot of server companies, they try to change themselves. So Noam Joby is right now with Google in developing the tensor processing unit. So, but his contribution is really a lot in terms of the processor design. And this paper is very influential. So let's see. And if you read this paper, you must remember these 4 things that he mentioned in the paper. So right now, I want to ask you one thing. How many of the following schemes mentioned in the paper do you think that would help AMD's processor in improving the performance? And I don't think I remember to put the timers on it. So you should assume that we have 90 seconds to finish the question. So go ahead, do it. Oops. All right, let's wrap up in 15 seconds. Five, four, three, two, one. Time is up. Okay, so let me not misleading you with the poll. So why don't you guys go ahead and discuss with your friend for probably about 2 minutes and share your thoughts again pretty soon. All right, let's wrap up in 15 seconds. Five, four, three, two, one. Time is up. Okay, so we have a pretty close tie between C and D. So right now, well, because I forgot to put the render generator on the slide, so I just want volunteer. I love volunteers, right? Which team right now is open to public? Everyone who think your team has the best answer, please raise your hand. First come, first serve. Which team? Come on, I need you guys. All right, so Joe, which team are you representing?
Team Valor. Valor.
Okay, so team 3. Okay, so what do you guys think?
We thought that D was the correct answer.
Okay, so what are the 3?
Victim cache.
Okay,
Victim
and
cache.
why do you think victim cache could help?
We think that victim cache reduces conflict misses if
Okay,
it's present.
so can you help me? Okay, so right now the following lectures, it will be you and me. Sorry, I don't want to torture you with this, but I just want you to show your understanding about like what victim cache is, right? So this is victim cache, right? So as you all know, victim cache is a small cache that can capture the evicted blocks, right? So it works like this. So first of all, right? So when you load store data, right? The victim cache would get a stuff from would try to get a well. So first of all, you will try to get a stuff from L1 cache, but if it's missing, right, then you will have to evict something, right? So you get the evicted block. Let's say the current evicted block is dead B, right? So let's put that in a victim cache. And in the meantime, because victim cache has a limited amount of storage. So for example, like Aslan Finan has 8 entries only. So we just put this. We have to kick out 1 block and write it back to L2. And in the meantime, we go to L2 to search for the block. And if we are fortunate enough, then we found it there. The return block will be in the L1 cache, right? So in this case, how do you think the victim cache could help for the case?
In this case, I think it will improve hit latency and hit latency, at least for like direct map cache.
Yeah, but for the pieces of code that we are looking for, why do you think it will help?
It will reduce the it'll reduce the conflict misses. Is that an answer?
Yeah, but can you give me a concrete example for that?
Reducing conflict misses? Okay.
A concrete example.
I'm not really sure about this one.
Okay, so what happens is that, right, the good thing about victim cache is that, well, if the next time we are looking for the same address that has been kicked out, right, and it's still missed in L1 cache, however, because we can found it in victim cache. So we don't have to wait for the L2 to respond, and we can just directly get a block from the victim cache and swap it with another block within the cache, right? So that's how victim cache works.
Oh,
right?
Okay.
So if you go back to our matrix addition example, right? Then let's say we know that we have A something, B something, C something, right? And then we have A something plus 1, right? So in the past, when I have the C something coming in, the A something will be kicked out, but now it's going to be in a victim cache. So when I access the A something plus 1, then you can find it in a victim cache, right? So that's the concrete example that I'm looking for from your answer. All right. So victim cache. So that's one thing that you think that would help. What's the other thing? So let's go back and look at this question.
Okay, so the other thing, prefetch.
Prefetch. So what is prefetch?
This is a method of mapping which block comes next and then putting it in a buffer so that
Or
you
say
can use,
predicting, right?
yeah, a
You are
predictive
predicting what's the
predicting.
next to come up, right? And so
Yes.
the basic idea of prefetch is that, like, for this pieces of a code, we know there's well, we can observe, right? This the address is mainly sequential, right? So we could actually you know, like create we could actually capture the pattern of access and use this pattern to predict what's going on, right? So for example, and what would happen is that, right? So right now I am missing D0 and I have a miss, and in the meantime I access the L2 cache and get a stuff, right? And then I have D1 miss or whatever, right? So that's the original pattern, right? But you can always find out, wow, whenever I have a miss, it must be happening on the edge of, you know, like D8, D0, D8, D16, right? So if your processor has some kind of logic that is smart enough, then you can potentially do this. Like I can issue a prefetch right after D0, because I know after D0, the next thing that you want must be D8. So when you serve the L2 access of these, after you finish serving that, right, the L2 can keep serving the next block. So when you really need the D8, it's already returned from the L2. So you will feel like, wow, the stuff I want is always there. And in the meantime, you can keep prefetching stuff. So the rest of the access will be really smooth. So that's the power of prefetching, right? All right. So what's the other thing that you think is correct?
We think that streaming buffer is also correct.
Okay. So what is stream buffer?
This is, I think this is more like a hardware thing where we have, this goes with the prefetch. So when we have to take something from from a cache, and this, when it returns, it is placed into the stream buffer instead. And so even though the original cache is there, you can read the block which is in the stream buffer.
Okay, so the string buffer, right? String buffer is more like a prefetch buffer, right? But what's different from prefetch is that prefetch can have very fancy patterns, but string buffer always put the next block into your into this string buffer, right? So it's only useful for sequential access, right? You cannot use prefetch. You cannot use very fancy prefetch. But for this pieces of a code that we are looking for, because the memory access is really, really regular and it's really sequential. So string buffer would help. And why don't you guys think about like miscache would help?
Okay, so I like we at least when we were discussing in the group, we didn't really know what missing cache was, so it was kind of a hit or miss on these three at least.
Okay, so what is miscache? So miscache, if you read a paper, it's pretty similar to victim cache, and victim cache is actually an improvement from miscache. So the basic idea of miscache is this: whenever I have an access, right, and I just put the miss block both in the L1 and the miscache, so it just duplicates the entry that you are looking for. You missed, right? So whenever you have another low store, it's highly possible that well, and if if this block has been gone, then you might be able to find it in miscache, right? So that's the whole idea of miscache. So if you compare miscache and victim cache, you will figure out that they are pretty similar, and both of them would improve conflict misses. However, victim cache is a version of missing cache that can help us to use the limited number of entries in a cache more efficiently because you are just swapping cache blocks when you have a miss. However, miscache always maintain duplicated copies, but and victim cache can capture the conflict miss better, right? So if you think about that, right? So you will figure out one thing is that, well, all of them, because so this is addressing, both of them are, both missing cache and victim cache, they are addressing conflict misses. So they could help the AMD processor very well. And for stream buffer, right? For stream buffer, it also tried to accommodate the prefetch block in an additional place. So it also helped us to, and because AMD processor has a pretty good spatial locality, so it kind of helped us in a certain sense in improving the compulsory miss case. And prefetch, it's kind of interesting that prefetch also improved the compulsory misses. So in fact, if you look at the pieces of a code that we have in the AMD processor, and thanks, Joe, for your answer. And thanks for walking through this example for us and your encouragement of showing your understanding. And for prefetch, right? Although it doesn't have the buffer, but it also helped to improve the compulsory miss. And one thing you might be aware is that even though AMD Phenom 2 processor has 100% miss rate, 6% of them are coming from compulsory misses. So this too will help the compulsory miss part. However, a majority of the miss are coming from the conflict. So the truth is that all of them will help the performance. However, these two, they help the most. And if you really pick one among these two, victim cache is more efficient than missing cache. So AMD processor, the AMD's Phenom processor, they actually have a victim cache to accommodate the case that we just seen. So that's why this paper is essential. All mechanisms that has been mentioned in this paper, they are really helpful to the case of AMD processor. However, the most effective one would be the victim cache. So if you can only pick one thing to do, AMD pick the victim cache to implement. So that's the answer of this question. All right, so that's about the prefetching. So one thing I want to share with you is that prefetching is actually a technique that could be, it's also a technique that you can use the software to decide what to prefetch. So the basic idea of prefetching is to identify the access pattern and try to proactively fetch data. That's on the hardware part. And the hardware will have a table that keeps track of the distance between misses, and that's called stride, and try to capture the pattern. So the hardware itself is kind of like doing its own machine learning to figure out, well, what's the next address. However, sometimes the software programmer, you know your access pattern better, so you can actually do software prefetch. And remember, in our RISC-V architecture, there is a spatial register called X0. No matter what you do with it, it's always 0. So you can use load instruction to load data into X0 to fulfill the prefetch. However, for processor like x86, there's not a spatial register called X0. So they also provide prefetch instructions. So they have a prefetch instruction that your program can use. And GCC has some kind of flag that can help you to prefetch the loop arrays that automatically insert the software prefetch instructions. So right now, I am going to give you a demo regarding how effective the prefetch is in the context of a sample code that I created So let me see. It's going to be, okay, let me share another screen. So share this one. Okay, so right now, if you look at the code that I am showing, there is, okay, so I have a matrix transpose code. So this is a matrix transpose code, and it's very complicated, and I have two versions. So one of the versions is called enable prefetch, and as you can see, I use the prefetch instruction, and I try to prefetch the next row, right? Because I'm here to add a row size. So what I do is that I prefetch the next row. So when I'm doing matrix transpose, and I don't think I have to explain matrix transpose a lot in the class because this is a grade level class, right? So let's right now make this two different versions. So let's say I have a regular matrix transpose code, and let's see how much time it would take. So for if I am transposing a big array, then as you can see, it would take about 3.25 seconds. And now if I use prefetch, right, it will help us to reduce the execution time a lot to just 0.6 seconds. So as you can see, it's almost like 5.5 times more speed up if you know how to use prefetch correctly. So it sounds to us that the prefetch is a very powerful tool. The software programmer can always use to improve your code, but is that really the case? So why don't you spend some time to thinking about how many of the following code snippet the prefetch can work effectively. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so right now, I don't want the poll result to mislead you. So why don't you just go ahead into the group discussion, and I already sent out the screenshot of the question. All right, wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so now I just want to pick one group. Oh, it's Mystic again. So let's try this for fairness. Ooh. Oh, Valor. Okay, so we have their answers. Right, so it looks like all right, Mystics. Okay, I gave up. Okay, I think that's what we really want to hear. Okay, Mystics, someone raise your hand. Who is the scriber of Mystics today? Who is the scriber of Mystics today? What do you guys think? What do you think? What do you think? Okay, Andrews.
Hi.
Hi.
Our answer either be 1 or 4, I guess.
1 or 4. So you think, wait. Say, what's your answers again?
So either be B or E, because we're not sure if prefetch one address is worth to do so or not.
I don't quite understand. I don't quite get it.
So
So
I think, so number 2, the while loop one, is definitely will be helped because the memory accessing is linearly. So every time some non-fetched or non-cached item can be prefetched.
So the second one is very clear, right? So how about the first one?
The first one, since it's a linked list, so the address of the next node will be not consecutively, so it's going to be on the other part of the virtual memory. We're not sure about if fetch one address will be effective because
Okay,
every time
you
the
are not
jump is different.
sure, right? You are not sure, right? So do you think if it's something that you are not sure, do you think it will be effective?
In my personal opinion, I don't think so, because if you
Okay,
prefetch it,
so here's the thing, right? So prefetch, you must be getting something that you know that it will be accessed to the next, right? But we have no idea where the next place is going to pointing to, right? And if you can definitely say that I always grab sufficient amount of stuff in my cache and then it will hit anyway. However, right, how do you know how long, how much time you have to wait for the prefetched data to be access. And the other thing is that don't forget you have limited capacity. So when you prefetch, you also kick out someone, right? So it's very possible that when you prefetch something, you may kick out something that you really need in the near future, right? So prefetch won't help the first case because the next pointer is hard to predict. And the second one, as you mentioned, is true that it's easy to predict. So prefetch could help easily. So how about the third?
I think the third one will be the same case as the first one.
Right, so it's also hard to predict. How about the fourth one?
The fourth one, I think it's the same because the
although it
address is
looks
not
regular,
consecutive.
but if you look at the address inside, right? So this is actually a variable and it's very hard to predict as well, right? So for this question, only one of them could help. Right, so prefetch is not as effective as you could imagine in this cases. All right, so thanks for answers from Andrew, and I hope you understand that. Well, it seems like prefetch is very smart. However, if you don't write your code regularly like this, there's no way prefetch can help. So being a programmer, sometimes you think I want to use fancy data structure to demonstrate my understanding about algorithm. However, this is really a disaster for performance optimizations. All right, so this is a grade level class, and so I want to tell you more about like what other hardware stuff that we have been doing to help improving memory performance. So the first one that I'm saying is that, well, conventionally, the hardware design is like this. We have a blocking design to simplify our state diagram. So what would happen is that we treat the whole DRAM as a single module or the whole cache as a single module. So whenever I have a miss, I want to fetch a block, I can only wait for the access to be served before I can serve the next request. So it's always the case that in the traditional blocking cache design, you fetch the block, you return a block, then you can fetch the next block and you will get the next block. And this all happens sequentially. So, but this is very inefficient, especially if you consider that we have multiple cores, we have multiple processors, we have multitasking, we have our processor speed is really fast. So what we really do right now is that we make our cache or our DRAM multi-banks and non-blocking. So by multi-banks, it means that we partition the physical organization of our RAM modules, no matter it's DRAM or SRAM, into multiple banks. And each banks, they are considered as individual unit that can serve requests separately. And in our cache side, we also create buffers and state machines for each entries in a buffer to make sure that we can perform access asynchronously. So what would happen is that because we have multiple units, so although each unit can only serve one request at the same time, however, if the next request does not belong to the same bank, then you can issue that request immediately after you issue the first one, and then both of them could be served concurrently and returned back to back. So in this way, you can see we can use the same amount of memory chips more efficiently. So if you want to draw it in a timeline, this is another analogy. So previously, you can only sequentially access your memory like this. But now with multiple banks and with non-blocking caches, if your request is fortunate enough that they are distributed into different banks, then turns out after you send the first request, you don't have to wait the first request to finish. You can immediately send a second request to the other bank, and etc. etc. So you can almost parallelize all your access in this way. So this is the multi-bank access. So another thing that I want to mention is that most of our well, so far in the class, I simplify the process of handling a miss a lot. However, as some of you might already experience, is that when we talk about miss penalty, when we increase the block size, right? Why accessing a larger block takes more time? Because the bandwidth between each memory unit is actually limited. So for example, because processor, each register is only 64-bit, there's no, it doesn't make sense for the processor to have a wider interconnect between the processor core and L1. And for L1 cache, because we are not always fetching the next block from the L2 cache, and presumably we should do this as seldom as possible, right? So and because we want to save the cost, so, and for hardware people, saving the cost is the most important thing. So so what we also have a limited bandwidth between the L1, L2, L2, and DRAM, or L2 and S3, L3 and etc. Right, so you cannot always, and thinking about the size of our block is really huge, right? So so what would happen is that, right? So whenever you have a miss, I thought I need to get a whole block before I can serve the request, right? So what it really turns out is that I have to write back, I have to fetch the block, then I can return the block. So what would happen is that when you have a miss, you have to write back different chunks of the block that you are evicting, and you fetch the block. And after you fetch the last chunk of the requesting block, you can finally return and restart. And so an optimization called early restart and critical word first is like this. So, well, when I write back, right, I still have to write back the whole block before I can restart. However, when I want to return the data, and remember, your processor only need one word from the block. So whenever I receive that word, right, if the word that I'm looking for is within the chunk that I already fetched, I just restart. And in the meantime, I keep fetching the next few chunks of the block. So that's how early restart and critical word first would help, right? So in this way, you can see, well, whenever I have a miss, it's still a miss, but I don't have to wait for the whole thing to, whole process to finish to restart, right? So now we still have the issue that, well, even though we can restart earlier, we still have the issue here, right? So this is a big chunk because we have to write back. So how can we alleviate this, right? So the write back overhead is right now the bottleneck of handling a miss. So the answer is that we add a write buffer. So the basic idea of write buffer is, again, small amount of caching. And whenever you have a write, you have a miss, you just write to the small write buffer really quick, and then you can fetch the block. So what will happen is that whenever you have a miss, you just write to the buffer. And because the buffer is really small, so the access time is really fast. And then you can issue fetch request, and whenever you got your chunk, you restart. So that's how write buffer would help in the case of handling a miss. All right. So and another good thing about write buffer is it might be the case that you have some data that are frequently updated. So for example, like the AMD processor that we, like the Colpit Snipit that we mentioned, right? Like we always like CI equal to AI plus BI, right? So it's highly likely that whenever you modify CI, the next one you are going to access CI plus 1. And because they are within the same block, so you can potentially merge them in a write buffer before you really write it down to the next level memory hierarchy. So that's how good, that's a good thing. Oh, another good thing about write buffer. But what I really want, so this, we have learned a lot of things, right? So, but what I really want you to think about is this summary of optimizations. So regarding this hardware optimizations, how many of them are really helping the miss rate? All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so right now, let's go ahead and have a group discussion. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so our random number generator select team 1 for answering the question. So can I have someone from your team to raise your hand and share your thoughts with us? All right, so I have Vion.
Yeah, hello, Professor.
Hey.
So, yeah, I think prefetching will help to reduce
Prefetching would
the,
help. And what type of mist could it help?
yeah, so basically in the initial phase when we have that compulsory, so no, not the,
So prefetch would help removing the compulsory mist, right?
yeah,
So why, how about other 3?
yeah. So other 3 are basically what happens are the processes to speed up your miss penalty. So when the
Okay, so
miss
it's
occurs,
improving
yeah.
miss penalty, right? And how about critical word first and early restart?
Yeah, so it is also the same. Basically, when you don't have the
Right,
word,
so it gives you the word faster, right? And prefetching, we reduce compulsory miss. And how about write buffer?
same thing. Like
Okay,
it,
it's also help us to reduce miss penalty, right?
right.
So for this question, right, we talk about a lot about the optimization, and the hardware optimization, only prefetching can help us to reduce the compulsory miss, right? So hardware can only do, and thanks for your answer is really great. So as you can see, hardware can only do limited things in improving our cache miss rate. So so from this one, you know that, well, hardware, there are limited things that the hardware can do. So that's why computer scientists, you guys have to know how to optimize for memory performance. And the first thing that I want to talk about is like, capacity miss is also one of the important miss. And a lot of you think about, like, if you want to squeeze the data into my cache, the first ever thing that I have to do is to reduce the memory footprint or the data set size that my code is using. So the first question I want to ask you is that, being a good programmer, do you really know how big the data will be in your memory? So spend 90 seconds, go ahead, look at this structure and tell me what's the size of this data structure. All right, let's wrap up in 15 seconds. Oops. 5, 4, 3, 2, 1. Time is up. Okay, so right now, let me see. It looks like, all right. Okay, so that's, let me send out this screenshot real quick. And right now, let's go into the group discussion. All right, let's wrap up in 15 seconds. All right, 5, 4, 3, 2, 1. Time is up. Okay, so looks like we have a tie on the result. So let's pick 110 to tell us the answer. Okay, Instinct, you guys got it again. Someone in group 1, raise your hand. What do you guys think? Okay, if not, now open to the public. Which team do you want to answer the question? Raise your hand. Okay, I have Joe. You are team 3, as I remember, right?
Yes. Yeah.
Okay, what do you think?
Our team had decided that the answer would be 40.
Be 40. How? Why? How come?
Okay. So the size of the doubles in the struct in the members, they are that's 8. And also because of alignment and the pointer, I mean, because of the alignment, and padding, all the others would also get 8 bytes as.
So what's the alignment? What's the alignment?
Pointer alignment is done so that it takes that 0 address. It's easier to access.
Yeah, but what's the idea of alignment? So you mentioned something called alignment. That's really good, right? So in x86, in many instruction set architecture, there is an alignment required in the instruction. So if an access is requesting an object of size n at address x, this x must be mod n equal to 0. That's called alignment, right? So if I'm accessing an address like x mod 8, and if this pointer or say this data type is a bytes, right? It must be mod 8 with 0. And if I'm accessing something with size of 4 bytes, mod 4 must be 0. So don't ask me why, but it's really because the hardware can do this faster, right? So so let me show you this demo now that let me share this demo with you. So if you still don't trust me, right? If you still don't trust me, let me show you this pieces of code. This is the oops. Oh, so this is another pieces of code that I want to. Okay, so that's probably this. Okay, I think I got the wrong demo. So programmer. Well, okay. So I will show you the demo later. But the truth is that because we have to we have the alignment issue, right? So what will really happen is that because when you access saying that this address is 0, right? Then when you access this ID, well, we know for access mod 0 mod 4 is 0, so we are fine, right? But however, the next is homework, and it's an 8-bit pointer, right? So for pointer, you really need the next address. So if you start with 4 mode A is not 0. So it can only start with 8 as the next address. So if you keep doing this, you will figure out the whole data structure would take 40 bytes instead of 32 bytes that a lot of you might think originally. So being a programmer, how to align your data structure better would actually affect the capacitiveness, right? So that's really important. And thanks, Joe, for your insights. Okay, so I will give you the demo next week and in the next lecture. And if you don't believe me, the source code is right here. So why don't you just create a code and try it yourself? So now, before you leave the classroom, several things I want to share with you. Assignment to do tonight. Assignment 3 is will due next Monday. I will put it up after assignment 2 is due. And the reason why we have assignment 3 due next Monday is because we have the midterm starting from the next week. So it's better that you get practice to the material that we will be covering before the midterm. And there's a reading quiz due Wednesday, and the project is already up because a lot of you were asking about like what's the project about. So I just put it up. You can already go through the detail there. And because this is a grad level class, we are not going to spend any minute in the class to talk about the project. So it's all on your own. And if you have a question that I won't mention in the lecture, please go to my office hour or the TA's office hour. Other than that, enjoy the rest of your day.